Hello, welcome back. This is section 16.1 and we're going to go all the way to 16.3 in this video. If you have just watched the chapter 15 review, you should probably do the problems for those first and be done with all that before you even watch this. This is going to lead us into what you're doing in the next week, if that makes sense. So you're still going to watch this by next Friday, but you won't need to use this for the assignments this week. I hope that makes sense. This is getting us ready for the next chapter, 16.1. After chapter 16, we will be doing some AP Classroom stuff as well. So this is a pretty important chapter. As I said, you guys are kind of the guinea pigs, so this is the second video I've ever made. There might be some weird audio things or clicking noises, that whatever. So 16.1, the principle of superposition. So this picture is saying that if you throw two baseballs across the same point, you guys know they will hit each other, right? Like we got this ball going this way, this ball going this way. If it was perfectly timed and they cross the same point, they're gonna hit each other and be deflected, right? That's pretty straightforward. This is true for like particles and physical things like that. The weird thing is that with waves can be in the same spot as another wave, and it doesn't affect the single wave by itself, if that makes sense. Waves can pass through one another. If you have two speakers like this, which, I mean, some of you might be listening to this on speakers, but if you have two speakers, this speaker, and they're releasing noise, this guy is going to hear both of them. If this wave hits this wave, it doesn't completely cancel it out. It's not like Alan can't hear that anymore over here. The waves go through each other. And that's kind of strange. There is some weird things happening at this point, which we'll talk about probably at the end of chapter 16. But in general, this guy over here, he's going to be able to hear both of these. It's not like the baseball where it gets stuck and knocked away like that. This is called the principle of superposition. So when two or more waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the displacements due to each individual wave. And I think a lot of people actually like learning this part because it makes sense, and it's not some weird like conceptual thing. It's exactly what you think it's going to. If you have a wave here and a wave here, and they meet each other, you now have one wave that's this wave plus that wave. It's just that big. And the interesting thing about superposition and waves is that they just pass through each other like they didn't even know they were there. See, wave 1 and wave 1, they just continue on. Wave 2 just continues on. When they meet each other, they overlap. But after that, they might as well have never met. Like, it doesn't matter. This gives us some interesting concepts. To use the principle of superposition, you must know the displacement that each wave would cause if it were alone in the medium. Then you must go through the medium point by point and add the displacements due to each at that point. So here we see two waves approaching each other. The first picture, at t equals 0, these are snapshot graphs. At t equals 0, we got this little triangle and this square. Nothing's happening. 1 second later, they technically haven't even met. But notice that this displacement for this triangle wave is 0, but this displacement for the square wave is, let's just say, a positive 1, right? Once you go for t equals 2 seconds, they are now on top of each other, right? And you can see this crazy house-like structure. The superposition of two waves is called interference. And if two waves meet like this and they make something bigger than themselves, it's called constructive interference. When both waves are positive and the total displacement of the medium is larger than it would be for either wave separately. So what we do here is we literally add the displacement for this triangle on top of the displacement for the square. So if we go back, see how this triangle is approaching this thing? 1 second later, this triangle will be taking up the spots from 2 to 4. And 1 second later, this guy will be from 2 to 5. So there's this overlap right here. And this overlap right here just gets added on top. So now the wave actually looks like this at t equals 2 seconds. That's constructive interference. And even 1 second later at t equals 3 seconds, the triangle is now right here. Which means for this half of the triangle, it thinks it looks and it thinks like it's just at its regular spot, right? But this part of the triangle thinks it's regular, but thanks to the principle of superposition, this part of the triangle is on top of the rectangle wave. This is still constructive. It's just not as pretty as this house thing. It's just a weird... I feel like if I put a dot here and a smiley face, I'd make a fish. Maybe I'll find a way to do that later on a program or something. And then 4 seconds, they are separated and nothing seems to be happening. This wave's going to continue on, this wave's going to continue on, and that's superposition. All it is adding on top. So if that was constructive interference, we also have destructive interference. And that's when one's positive, one's negative. Once they overlap, they actually are going to start canceling each other out. That doesn't mean that the wave disappears, it means it looks like the wave disappears. The waves will still definitely be there, but it's possible that they cancel each other out for just a split second to where it looks like there's no wave. So here we see at t equals 0 seconds, they're heading towards each other. Here at t equals 1 second, this wave that goes from 4 to 6 will now take up the space from 3 to 5. And this wave that goes from 1 to 3 will now take up the space from 2 to 4. Which means from 3 to 4, there's this overlap, right? This is where the top wave wants to be. This is where the bottom wave wants to be. So what you do is you literally add the displacements. The displacement right here is all of this positive and there's no negative, so we still stay up here. But let's look at this weird point right in the middle. It goes up right there, but this also goes down right there. And it goes up and down the same amount, just negative, which means we end up right in the middle because this positive plus this negative would equal 0. Over here, right at this like halfway point, there's a little bit of positive right here, but most of the wave is negative, right? Most of the wave is negative. Which means you add this little positive part to this whole negative part, and then you get the line from here to this dark line. If we go 1 more second later, we get these two triangles on top of each other. Or, a half a second later. These two waves are now directly on top of each other. This positive is the same as this negative, so it cancels out to 0. This positive is equal to this negative, so it cancels out to 0, 0. So this whole wave right now looks like it doesn't exist. If you just took this snapshot graph without these dotted lines and showed someone, it would just be a straight line. A half a second later, though, it looks like this again, just in the opposite direction, because this positive one is going to the right, and this negative one is going to the left. And here we need to add up the displacements. So from here to here is a certain positive, from here to here is a little bit of a negative, so you take that little negative down and you end up on this dark blue line to what the actual wave says. For your homework that'll be coming out next week, you guys are going to be doing a decent amount of these. And both waves emerge unchanged. Go ahead and stop, take a second, pause the video, look at this question, and see what the answer is. And the answer is C. If you didn't get that, go back, see if you can figure it out, or bring it up during the video lessons. The reason why I'm not going to explain these is because the last video took a half an hour, and I don't want to make you guys listen to my voice like that for half an hour. So we're going to try it for this video, pause the video during the example problems, try to figure it out, and then go ahead and play the video. Similar to what we would do in class. So go ahead and pause this. And the answer would be B. So go ahead and pause this, try to figure it out, and then press play once you think you got it. The answer would be A. That guy right there is right there. And this part is kind of winning over here. Alright, 16.2, standing waves. It's possible that you can trap a wave in a string like this, and waves that are trapped and can't travel in either direction anymore are called standing waves. Now remember, with waves, individual points on a string oscillate up and down, but the wave itself does not travel, which means this piece of material, or materical, this piece does not ever make it over here. It doesn't travel. The wave travels. The wave travels through the string. And this is called the standing wave because the crests and the crests and the troughs seemingly stand in place as it oscillates. So we got this sinusoidal wave coming from the right, this sinusoidal wave coming from the right going left. This one is coming from the left going right. When they interact, there's going to be a bunch of different types of superpositions, right? So this graph is kind of crazy. We got this stuff. The red line is going to the right, and the orange line is going to the left. All right. So if we add up the displacements, we get this blue line. Okay. So notice right here, this is the most positive all of them are, so it ends up being that the blue line's up there because this is positive and this is positive for both the red and the orange. So it ends up being all the way up there. Notice this is the farthest down, both the red and the orange go together, so negative and negative make this deep negative. At t equals 1/8 of a period, we see that these two waves, although they're going opposite directions, have now actually met, right? They're now directly on top of each other. So what that looks like is this is adding the displacements in the positive direction twice to get all the way up there. This is adding all the negative displacement twice, so it ends up going down there. And we see that that means this is kind of the 0 points because there's no displacement on either of the waves. At t equals 2/8, it looks like this wave again. But you'll notice the colors are reversed. That's just because the waves are moving, right? Now this orange one, now this red one, I'm sorry, is over here, and now this orange one is over there. And we see just the colors reversed here. But if we keep this going just a little bit farther, you'll notice that the top of the red will be with the bottom of the orange. If the top of the red is matching with the bottom of the orange, and these are the same waves, they will cancel out to be flat. Right? Because according to the superposition, this is all, the entire wave, I'm sorry, both waves are producing destructive interference. So our actual string, our actual blue line, will just look flat. And here's what it looks like if we didn't map each one of these waves separately. If we just saw this happening, we're just taking pictures at 0, 1/8, 2/8, and 3/8 t. We get a kind of normal looking wave, it gets really big, it goes back to kind of normal, and then it goes flat. If you can guess what would happen next, it would start back up here, except the opposite direction. So this is going down, this next one, it would start going up. And we see that right here. See how this is flat? Next this is going up, really up, not as much up, flat, and then it goes back down, which is back to where we started right here. So it kind of wobbles like that. The two waves are represented by orange and red line. At each point, the net displacement of the medium, which means of the blue string, is found by adding the red displacement and the orange displacement. The blue wave is the resulting wave due to superposition. Okay, so the red and the orange waves, you wouldn't actually be able to see those in real life. All you would see is the result of them added together in that blue line. At this point, you should pause this video, go to the description of this video, and I posted a link to a guy. I'm posting a link, in case the link doesn't work or whatever, it's this guy, James Dan. So anyways, part 1. He goes to a really good video explaining this. Again, the reason why I'm not putting that in this video is because it'll make this video longer than it needs to be. And that takes a decent amount of effort for my computer to upload some of these things. So this is assuming you've watched that guy's video. You've watched the guy's video, you've seen the actual waves on that string in person, not quite in person, but you know what I mean. So in a standing wave pattern, there are some points that seemingly never move. And not just seemingly, they don't move. They never move. These points are called nodes, and they are spaced a wavelength, a half a wavelength apart. So if we could, like in the video, trap the wave right here, that's a node. Over here there's a node, over here there's a node. So it's always a half of a wavelength. That's where the nodes have to be, always a half of a wavelength. And that makes sense, right? Because if we start here and we go like this, that is one wave. Right? This is one wave. So this has to be half of a wavelength. And if these are nodes, then these are called antinodes. That's where there's the maximum displacement of oscillation. So nodes is where there's nothing. Antinodes is where there's the maximum displacement. The wavelength of a standing wave is twice the distance between successive nodes or antinodes. So if you did not know, if you just were presented with a standing wave and you didn't know the wavelength of this thing, all you would have to do is take a snapshot and measure from here to here, measure that distance, and that has to be a wavelength of the standing wave. Like that has to be. It's not like you have to figure it out or anything. This to this, that distance is a wavelength. The wavelength is twice the distance between successive nodes. Or even antinodes, if you want to do that. I don't know why, but from here to here, that's also a wavelength, right? From here to, that's one wavelength. This is just saying the nodes have zero destructive interference at all times. The intensity is maximum at points of constructive interference and zero at points of destructive interference. So this is the most intensity, as you can see with this graph, and this is the least intensity of being actually zero. So go ahead and look at this, pause the video. The answer is C. You can see from here to here, that is one wavelength. Alright, last section. 17 minutes in. A little longer if you watch the video and pausing and stuff, but that's what we got to do for online, right? Let's keep going. A wave pulse traveling along a string attached to a wall will be reflected when it hits a boundary. All of the wave's energy is reflected, hence the amplitude of a wave reflected from a boundary is unchanged. So this wave goes here, it hits that, it does some physics things and goes upside down and is reflected, but the amplitude's the same. Of course, this is in a perfect world, assuming no friction and everything behaves exactly the way we want to. But the amplitude does not change, but the pulse is inverted. And this is interesting. Waves also reflect from anything that is a discontinuity, which means a point where there is a change in properties of the medium. So if you have a string that's pretty thick and then it gets to a thin string, that's a discontinuity. The characteristics of the thing carrying the wave has changed. So it's no longer the same. That's what it's discontinuous. I just want you to know I've been pointing at the screen as if you could see what I'm pointing at. It takes a bit to get used to this online teaching stuff. Once it hits here, we see it does get bounced back a little bit, but most of the wave goes over here. This has a string with slower speed. This goes faster because that linear density is less, so it's going woo, and once it hit here, this wave will go even faster. This one, not so much. Here's another example. This thin string going towards this. This kind of acts like a wall as far as this small string is concerned, so it inverts just like that picture here. It inverts, but then some of the energy does get to go this way because it's not technically a wall, right? But as far as this thing is concerned, it's a wall that steals a little bit of its amplitude. This happens a lot also with windows. So like at nighttime, if you have your light on, and you look out your window, it's probably just going to be a reflection of your room, right? That's because the light from inside of your room will pass through the window being the discontinuity. So when the light goes through the window, some of that light gets bounced back to your eyeballs, some of it goes out outside. So when you're looking at the window at night with your light on, you usually just see reflection because the light from outside isn't bright enough to overcome that reflection from the inside. Does that make sense? If you turn off your light at night, then you can see the stuff outside, right? So they have a picture right here. You can see it. This is the same thing. It's just at nighttime, if your light's on, the discontinuity of the glass reflects so much light that you cannot see the light outside because there's so little light outside. So it's important to realize that the glass itself is a discontinuity because it's different than air, right? So light traveling through air will act differently than light traveling through glass. It's discontinuous. So one way you can make a standing wave is to just wiggle a string in the middle like this. And if you wiggle it up and down like that, you're making the same wave, but this wave is going that way and this wave is going that way. So you wiggle it and it goes here. Once it hits this other part, it reflects, right? We talked about that in a couple slides ago. It hits this boundary and reflects. So now these waves are heading towards each other, but see how this was up? Now this is down. In order for there to be a standing wave, two conditions must be met. First, the displacement at x equals 0 and x equals L, which means the length of the string, must be 0 at all times, meaning these have to be fixed points, right? This has to be stuck here, this has to be stuck here. Stated another way, we require nodes at both ends of the string. We know that standing waves have the spacing of half of a wavelength between nodes. This means that nodes must be equally spaced. So that's something else. Nodes must be equally spaced. This makes sense? So here's a node and here's a node. So you can do that. But if you're smart, you're thinking, well, what if we just put a node in the middle? Then there's still a node here, there's still a node here, and all these nodes are still spaced apart. Well, this is an example of another standing wave that whatever this type of material can make. And here is 3. A node here, and all these nodes are the same length, so it meets the criteria that we just read right here. So all these are valid standing waves. So here we see 3 modes of a standing wave for a string. The mode number m helps quantify the number of possible waves in a standing wave. A mode number m equals 1 means that there's like 1 wave trapped in here. M equals 2 means there's 2 waves trapped in here. And 3 means there's 3 waves trapped in there. You can think like this is 1, 2, 3. Right? That was 3 wavelengths. If we do here, this is half a wavelength, and this is the other half, so that's 1 wavelength. This is 1 wavelength, and this is 2 wavelengths. So it's like how many waves are trapped in there. And each of these modes have a different wavelength, right? Because this is half of a wavelength for mode 1, but this is a full wavelength for mode 2, right? This distance L, for mode 1, L is half a wavelength. For m equals 2, L is a full wavelength. So for any mode, m, the wavelength is given by the equation, wavelength of whatever mode we're talking about, equals 2 times the length divided by whatever mode we're talking about. Right? 2 times this distance, so 2L, divided by 1 would give us the wavelength of 2L. And that makes perfect sense here because we said we have to go from here back to make 1 wavelength. So 2 of these L's, which is exactly what this says for m equals 1. For m equals 2, we were saying that to go from here to here is 1 wavelength, right? So 1 wavelength equals L. So if we plug in our stuff, 2 times L divided by mode 2, we get our wavelength being just L, which is what we said right here. That's L, right? Here it gets a little trickier, but the point still stands. We're in mode 3, and we said this right here is 1 wavelength, right? So 2/3, I guess. Just by like looking at that, we say 2/3. But if we come over here, 2 times the length divided by the mode. Well, mode are we in? We're in 3. So this is 2 over 3L equals a wavelength. That's exactly what we found out, right? Because from here to here, that is 2/3 of this whole L. We can also relate this to frequency using that equation right here. It's just written in terms of whatever mode we're talking about. We can replace lambda m for 2L over m, which is just what this is right here, to get m times v over 2L, and m being whatever mode we're talking about. So the mode number m is equal to the number of antinodes on the standing wave. And we can see that here. There's 1 antinode. There's 2 antinodes. There's 3 antinodes. So these standing wave modes are the frequencies at which the wave wants to oscillate. So we can try to make a standing wave with any frequency, but it won't necessarily work. But there are some that it wants to oscillate at. These are called the resonant modes or resonances. Like for what this string is, there's a specific frequency that the string wants to get to in order to do this. If you don't meet that, you're not going to be able to make this cool of a picture. It's just going to be kind of a wobbly string instead of a standing wave. And you saw that in the video of that guy. It doesn't necessarily, in the beginning it's just kind of all wobbly until he gets to those particular frequencies that match just exactly for the string and the length. So go ahead and pause the video. The answer is B. 1, 2, 3, 4, 5. Alright, so the first mode of the standing wave modes has the frequency of this. This is the fundamental frequency of the string. This is like the lowest, the baseline frequency you can get, okay? So we got the speed of the wave in that material divided by the length that we're talking about equals that bottom frequency that everything else is going to be built off of. Because all of the other frequencies that can make another standing wave, that can make these, are all just multiples of that very first number we found of this. So if we find the fundamental frequency, then all of the other frequencies, no matter what mode we're talking about, are just multiples. So just 2 times that initial frequency, or 3 times that frequency, or 4, 16 times that initial frequency. The point is, we need that frequency. We need that base frequency. We need this one. They're all integer multiples of the fundamental frequency. So the sequence of possible frequencies is called a set of harmonics. And if you're above m equals 1, then they're called the higher harmonics. So all of them would be the harmonics. The ones above 1 is the higher harmonics. Let's look at this example. A 2.5 meter long string vibrates as a 100 hertz standing wave with nodes at 1 meter and 1.5 meters from one end of the string, and at no points in between those two. Which harmonic is this? What is the string's fundamental frequency? And what is the speed of the traveling waves on a string? So I'm going to draw a picture right now. Not the one here, but we said it's 2.5 meters long, right? So 2.5 meters long. If this is okay, so we know that, oh geez. We know that right here and here at 1 and 1.5 there are nodes. That's what the problem said. If you try to draw a line right now from here like that, that wouldn't make any sense, right? You can't have a standing wave that looks like that because they're not all the same length, right? We said that they have to be the same length. So even though we don't have the positions of all of the nodes, the two that we do have help us find where the other ones are, and that's what they're showing you in this drawing. We have 1.0 and we have 1.5. We don't technically have these 2 points, but critical thinking says if there's a half a meter between these two, and all the distances between all the nodes has to be the same thing, then we know that this one's 0.5 away and that one's 0.5 away, and it all lines up like that. So then we can draw something like that. Now they're all even, but in this picture they are not all even. This would be very wrong. Don't do that. But that's one way to kind of check your work. Like, is the wave right? Well, if it's lopsided waves like this, then no, you did not do that right. Which harmonic is this? What's the string's fundamental frequency, and what's the speed of the traveling waves on the string? Well, we know the length, we know the frequency that we're at least right now. Not the fundamental, but we do know this, right? So we draw a picture, we fill in the nodes that we know need to be there, even though they didn't tell us. Let's count the number of antinodes, because the number of antinodes deduces the mode number, right? So there's 1, 2, 3, 4, 5 of these antinodes, which means we're in mode 5, so M5. Which means we know that this frequency is going to be this F1 right here. I'm sorry, the FM. Because we're in mode 5, right? So F5 equals 100 hertz. F5 equals 100 hertz. So we see that here. If F5 equals 100 hertz, and we know M equals 5, we're looking for this very first fundamental frequency. So we rearrange the equation. F1 equals our F5 divided by our mode number, so 100 divided by 5, and we get 20 hertz. So this is the frequency that we're at right now. This is the mode that we're at right now. If we divide the frequency we're at right now by the mode that we're at right now, we can find the fundamental frequency of this string, the lowest frequency that this thing can still make a standing wave. That gives us a lot of information. Let's look at our problem. What else do we need to actually find? Which harmonic is this? So fifth. What's the string's fundamental frequency? 20 hertz. And what's the speed? Okay, we don't know that yet. The fundamental wavelength we can find by lambda being 2L. Right? The fundamental. Remember, we're talking about fundamental now, not this one. The fundamental from here back to here is 2 times the length. Right? Because the fundamental mode looks like just one loop like that. I'm sorry, from here and then to there. So 2 times the entire length equals 2 times 2.5 equals 5 meters. So we know that the fundamental, not this thing, but the fundamental wavelength is 5, and the fundamental frequency is 20. So then we use this equation I told you guys not to forget, because it's everywhere. We rearrange that, and we just simply multiply 20 times 5. We get 100 meters per second. Notice we didn't use this, and we didn't even find the wavelength of our fifth mode string. We just broke everything down to the fundamental numbers, and then found out the string speed. If you stayed up there in the if you found the wavelength of the fifth mode and used the frequency of the fifth mode, you'd still get 100 meters per second, because the speed will always stay the same. These numbers are just going to be changing. This number will go up, this number will go down, but it will equal 100 no matter what. Oh, and it does that right here. 100 hertz multiplied by 1 meter, and we can see that that's 1, right? That's 1 wavelength, so that's 1 meter, so equals 100. So it's always the same thing. Just breaking down to the fundamentals might be easier sometimes. The fundamental frequency can be written in terms of the tension in the string and the linear density. So if you're talking about the fundamental frequency of a certain string, that's normally V over 2L, but we have a substitution for V based off of last chapter, we know that V equals the square root of the tension of the string divided by the linear density. This is really common in musical instruments. On many instruments, the length and tension of the strings are nearly the same, but the strings have different frequencies because of this thing right here. So example is the guitar, right? From here to the top, that's the same length, and they're pretty much under the same tension. Not quite, but I mean pretty much. They're all in the same device, so they're all under pretty much the same tension. The only difference is how thick the strings are, which is talking about the linear densities of the strings. So go ahead and pause this. The answer is C. Go ahead and pause this. The answer is B. But Atif, I'm sure you knew that, right? You probably said like it's either A, B, or C. And then, yeah, I know what you're thinking. Fifth string on a guitar plays the musical note A, the frequency of 110 hertz. On a typical guitar, this string is stretched between two fixed points, and this length of string has a mass right here. What is the tension? So it looks like we're going to be using this equation because there's tension right here. They gave us mass and length, which means we're probably going to be using linear density. Yeah, linear density right here, so mass divided by the length of the string. So in case you didn't know, mass divided by length equals this linear density. That's 4.47 times 10 to the negative third kilograms per meters. We can rearrange equation 16.5 for the fundamental frequency to solve for the tension in terms of the other variables. So here's it was squared before, there's linear density, there's L, there's F1. From here, or actually, from here. Oh, and once we plug all this stuff in, the answer is 88.6 newtons. So that means each string is about 88 newtons, so add all that up and it's a little bit more than 500 newtons. So we've been doing like physical waves, but it does work the same way for lasers as well. Lasers are just waves, light waves that we've trapped in a standing wave and then shot out like with all the same properties. So if we like shoot a little light beam inside of this reflecting chamber almost, and the light just keeps bouncing back and forth until it's all kind of in the same standing wave, but for light. You can do the same type of things with these problems, even though it might not feel like you can because it's light, right? Like it doesn't have the same, well, it is a wave, so we can still, it's a transverse wave the exact same way a wave on a string is, so we can use these same equations to solve for it. So we know the length of the chamber, we know the wavelength that was given to us, so if we want to find which mode it is, we get 474,000, that's what mode we're on. So high number mode seems reasonable because the wavelength is so short, right? Like this number, 10 to the 9th, that's one wavelength. So if our chamber is actually a measurable amount, that means it's going so many times. So the 474,000 makes sense. So that's it for that. You made it this far. Hopefully you didn't watch this all in one go, or if you did, you wanted to, because this video is 40 minutes long right now, not including pauses and stuff like that. So maybe next time I'll make a disclaimer saying you don't have to watch this all at once, but we'll see. Until next time.